My name is Justin Hutches, and I am the group leader for Group 2 doing the preparing experiment. Little introduction. The purpose of the experiment is it represents relations between saturation pressure and temperature, the change in entropy associated with phase change, and the specific volume of two phases. We can determine the enthalpy through measurements of pressure and temperature since it cannot be directly measured. And the objective of this experiment is to determine the latent heat of vaporization of water using the Clapeyron equation over a range of temperatures and pressures. In theory, latent heat of vaporization is calculated using the Clapeyron equation, which is dP sat over dt is equal to SFG over VFG, which is equal to HFG over TVFG. The ideal gas equation below it is very similar, as said before, but you're using your ideal gas constant. Your Psat is your saturation pressure, T is your saturation temperature, HFG is your latent heat of vaporization, VFG is your specific volume, and SFG is your entropy. Look at the apparatus, and now see my picture cut off. Number one, you're going to have your flask with a rubber stopper at the top. The rubber stopper is there so the thermocouple has something to sit in. And you have your lines running through to your tank and to your pressure gauge up top. Number two is your boiler, your hot plate heater, which is going to boil the water inside the flask. Three is your thermocouple, which is going to read your data back to your computer. It cannot touch the sides because then you'll get inaccurate data. Four is your omega analog pressure transducer. Five is your mechanical pressure valve. Six is your air bleed valve. Seven is your vacuum control valve. 8, your centrifugal pump, your water reservoir is number 9, which is cut off in this, and the computer system is number 10, where your data is going to be logged. Setup procedure, you're going to place the flask onto the hot plate and fill it up with 2 inches of water, and you're going to make sure your thermocouple is 3/4 of an inch below that water surface. You're going to make sure your water reservoir has sufficient water to cover both the inlet and outlet pipe openings from the pump. And then you're going to close the vacuum control valve and open to bleed air out of it. Once this is done, you can turn your pump on. After you've done that, you can close the bleed valve and verify that the stopper is drawn in firmly, because the last thing we need is that thing come shoot off the top of it. When the pressure is low, close the control valve and turn the pump off, and you're ready to begin the experiment. This is the procedure for the actual experiment. You're going to start by turning the vacuum pump on and bringing the flask to the lowest vacuum, leaving the valve open. You're going to plug in the hot plate and set to high, bringing the water to boiling at no pressure. You're going to make sure the thermocouple is submerged but not touching the beaker. As said before, this will mess up your data. You're going to begin logging the data after the water begins to boil. After that, you'll close the line off to the vacuum pump to cause the pressure to rise. You're going to check your values, your Psat and your Tsat values, to make sure that they're in line and you're not just varying off from what numbers we're supposed to be getting. You're going to open the air bleed valve before the pressure in the beaker reaches atmospheric. Once that's done, you can stop recording data and turn the hot plate off and allow the beaker to cool off. Shutdown procedure, you're going to close the vacuum control valve, open the air bleed valve, turn off the centrifugal pump and the heat and plate, disconnect the power supply, and clean up your work area so that it's ready for the next group to come in and do the experiment. This is my pressure versus temperature plot. I got these from the steam table in the thermo book that was provided. I ran it up from 5 to 190 degrees Celsius and from 0 to 1400 kPa, as shown with this linear regression plot. And these are my calculations. I used the Clapeyron equation from before and rearranged it to solve for HFG, which is temperature squared times the ideal gas constant times SFG over your saturation pressure times your specific volume. My first arbitrary point I picked was 25 kPa with a temperature of 65 degrees Celsius. I got 2354 kilojoules per kilogram, and the number that was in the book was 2346, so that was pretty close. My second value was atmospheric pressure and temperature 100 degrees Celsius, which gave me a value of 2261 kilojoules per kilogram. And the steam table set 2257, so once again, very close. And my third pressure was 700 kPa with a temperature of 165 degrees Celsius, which gave me 2070, and what was in the steam table was 2066. Some lab safety. We want to make sure we don't touch the hot plate and burn ourselves. We want to use gloves for any hot objects like the flask or anything if we have to move it for any reason. Safety glasses, goggles while performing the lab to protect our eyes, and wear pants and closed toe shoes. And these are my references.